Okay, here we go with the last example on this handout. And so this idea of this conical pendulum that I mentioned in the Zoom class on Thursday looks like this. And it's really going to be, like I said again yesterday, exactly the same setup and process. Get to a slightly different type of an answer, but it's the same exact process. It's just Newton's second law again, but now we're relating it to the this circular motion kind of an application. So if the mass, if the free body diagram looks like this, where we've got the mass over here, and then we've got a tension like this, there's a force of gravity. And what makes it go around in this circular path is obviously an inward component. There's got to be an inward component of tension in this radial or inwards direction that keeps curving it, so it follows a circular path. So like I did in the previous example with the car, if we think about a coordinate system that has a z-axis, then tension has a z component. And tension also has an inward or radial component. And if we think about like where does theta show up in our free body diagram, if I was to draw another parallel line to this one here, then this angle here would be the same as this angle up here. Something to do with geometry and alternate interior angles between parallel lines, blah blah blah. So anyways, it's this angle here that is the same angle as the upper angle with the string attached to the ceiling or whatever it's attached to. Okay, so it says I want answers that are in terms of L and V, and I don't know about M. Maybe M will be in there, maybe it won't. Hint, hint. So an expression for the tension. So we need to leave T in our work here. And so we are going to have a couple of knowns, and like we usually do, we're going to deal with the sum of the forces in the radial direction because that's what causes the radial or centripetal acceleration. We can also talk about the forces that are in the z direction because that's going to be our link to get rid of some unknowns. So going to the radial direction, in the radial direction we just have that t sine theta. This radial one is up at the top, so up top across from it, sine is going to be the mv squared over r. And if we look at it, maybe we don't even need to go to the z direction, but I'm going to do that real quick and then maybe we'll decide which one we would prefer. So tension component in the radial direction, tension component in the z direction, just did radial, minus mg equals 0. So tension in the z direction, let me back up a step, tension in the z direction would be t cos theta equals mg. So t equals mg over cos theta. Well, let's see. If it said we want to have our V involved and we want to have L for the length of the string, this one doesn't really kind of get us there. So if we go back to the other one, we need to do a little cleanup because I don't see L like it asks for up here. So what's our radius? Our radius here is going to be equal to L sine theta, the length of the thing. The length of the thing here is like the hypotenuse. So the radius is the opposite side, or sine of theta is the opposite side over L. So if we rearrange things, we get L sine theta. So I can plug that in over here. So T sine theta equals mv squared over L sine theta. And just doing the algebra of moving the sign over there, we get, we're going to divide it out. So it's going to be T equals mv squared over L sine squared theta. So remember, we've seen this somewhere along the lines, but sine times sine is sine squared, and it just like x times x is x squared, and it's notated like sine and then squared and then the theta for whatever reason, notationally. And nope, sorry, we don't get rid of m, but there's our answer for part A. It's not pretty, but it's been worse. I'm going to jump to the next page to talk about then the period of the pendulum. The period of the pendulum, we need to introduce T for period, so don't be mistaken by the T for tension that we were using before, but big T here is going to be the variable for the period, the time period of the pendulum. If you remember back to chapter 4, little t is used in the kinematic equations and stuff like that for just any elapsed time, that randomly elapsed time that could be introduced, like how fast is the car going after 10 seconds, or what's the acceleration at t equals 3 seconds. Here, capital T is usually used in things that repeat themselves with a regular periodic, meaning repeated motion. It happens in the same time frame over and over and over again. The moon orbits the Earth once every 27.8 days or something like that. So that's a regular periodic repetition with a given period of time between each repetition. And so capital T stands for that in general. So back to our sum of forces in the radial direction equals mv squared over r. The radial direction was that, I'm going to go back to Ft for tension. So I'm going to say Ft is our tension so we don't get confused by which T is which. So Ft sine theta, that's our radial component. Remember from back here, our inward radial component was tension times sine of theta over here. So going back over here, that is equal to mv squared over r. Well, how do I introduce the t in there? Remember that the tangential velocity is 2 pi r over t, the time period. So if I do that, so Ft times sine theta equals mv squared. Oops, I need my v squared, so I need to back up a second and say then v squared is 4 pi squared r squared over t squared. So all of this stuff squared. So this becomes a little bit ugly. So m times 4 pi squared r squared over t squared. That's just that v squared term. That's still all over r. So we can kind of clean up things a little bit by getting rid of the squared on the r and getting rid of the squared in the denominator. It doesn't do a ton for us, but it does a little bit. Remember this Ft is kind of an unknown here, but we can substitute in for what we had earlier. So from the previous page, the tension was equal to mv squared over L sine squared. So keep him with the black, mv squared over, oops, sorry, wrong thing. Hold on a second while I think for a second. The tension, easier, the tension with the with the z components, the tension is mg over cosine theta. That's a lot prettier looking than where I was going to go. So mg over cos theta is our substitution there. And we still have a sine theta, and that's equal to that monstrosity here. So m 4 pi squared r over t squared. And we can do a little cleanup again because there's some more extra r's floating around. Let me pause for a second. Okay, I'm back. A little cough, clear the throat break. This R floating around here. If you remember, back here we kind of eliminated R in having to put things in terms of L, and R is L sine theta. So I'm going to keep up with that as the way that the question was stated. So I'm running out of space, so I'm going to say this R. You can write this on another line if you want, but the R becomes L sine theta. So we're doing things in terms of L's and all of that, like they said before. Cleanup, again, continued. Get rid of the M's. Notice that there's a sine theta here and there's a sine theta here. And now it's just off to the races to solve for t. So if we do some rearranging, t squared should be equal to 4 pi squared times cos theta, run back through here, over g. Cos theta comes up, t comes out of the basement, g goes down to the basement, so put the g in the basement, and so the t then just becomes equal to the square root of all of that stuff. So it's not real pretty, but we're in AP Physics. So there's your answer. T is going to be equal to the square root of 4 pi squared cosine theta divided by g. Yeehaw.